Alrighty, kiddos, we got section 3.1, day 2, fun with derivatives continues. So, first question, what does f prime of x measure? Well, you have to remember what f prime of x means. It's the derivative of a function, f of x. So, as we've talked about a million times before in class, it's the slope of the line tangent to a curve at a particular point, which really, if you think about it, it's the slope of the curve itself in this teeny tiny little interval. It's the instantaneous rate of change of f of x, and it's the value of the derivative. That's what all these things mean. And if the graph is a distance versus time graph, then this would also measure the instantaneous velocity. Okay, so today we're going to be looking at graphs of the derivative. You can actually do that. You can actually graph the derivative function. So we're going to start by looking at an easy-ish example. Say we wanted to start with a function f of x is equal to 3x. So I'm going to first graph that. It's just a line. Y-intercept is 0. The slope is up 3 over 1, up 3 over 1, down 3 over 1. And we try really hard to draw a straight line through all those points. And we kind of mess, but that's okay. So this green line is f of x. Right, so now I want to graph the derivative. So what I need to do is I need to figure out at any given value x, what is the slope of f of x, or the derivative of f of x. So we start at 0. So at 0, I have to think, what's the slope of my curve, my line, right here? Well, the slope was 3, so it's 3. So I'm going to plot that point. At x equals 0, the derivative's value is 3. At x equals 1, what's the value of the derivative? Oh, it's 3. When x equals 2, oh yeah, the slope right here, it's still 3. So when x equals 2, the derivative is 3. How about when x equals negative 2? The slope of my curve, oh yeah, it's negative 3, or it's 3. So I come up here and I go at 3. So do you guys agree that no matter what x value I'm looking at, the slope of that line will always be 3? So if I plot those points, I wind up with the graph of my derivative. So f prime of x is just the line where y is always equal to 3. Or f prime of x is always equal to 3. Okay, so let's do a harder problem. Let's try to estimate what the graph of the derivative is going to look like for the function f of x is equal to negative x squared. We're going to do this using mini tangent lines, and it's really hard for me to do this on my computer. You're going to be able to do a much better job of this at home if you use a ruler or like any sort of straight edge, a piece of paper or whatever, to try to do tangent lines. So let's start at 0. Let's start at an easy point. So at x equals 0, what would be the slope of the curve at this point? Well, if I draw a mini tangent line, oh, that's fantastic. Let's undo that, shall we? Okay, so if I draw a mini tangent line right here, then what's the slope of that line? Oh, well, it's 0. Right? When x equals negative 1, if I try to draw in a mini tangent line like that, if I maybe keep it going, it looks like the slope is up 2 over 1, so it looks like it's a positive 2. Right? If I was at negative 1, positive 1, then the slope of my tangent line looks kind of like it would be down 2 and maybe over 1. So it looks like it would be negative 2. So if I continue doing this, at negative 2, if I draw in a mini tangent line, it looks like it's a positive and it's steeper. And it looks like maybe it's going to be 4. So at 2, it would be negative 4. And then it gets pretty tricky when I'm here at negative 3. Let's see, my value would be negative 9. It's super steep, right? So again, you're going to be able to do a better job at home with your ruler, but let's just say that it looks like it's about a 6, which means it would be the exact opposite on the other side. And notice all my derivative values are positive on this side of my parabola because my function is increasing, and then they're negative on this side of my parabola because my function is decreasing. A lot more on that is coming your way soon. Okay, so if I try to actually plot those values, let's see what happens. So why don't we do that in green this time. Alright, so at negative 3, it looks like the value of the derivative is 6. At negative 2, the value of the derivative was 4. At negative 1, the value of the derivative was 2. And at 0, it was 0. And at 1, it was negative 2. It was negative 2, and at 2 it was negative. Oh my goodness, do you guys see what's happening here? It's negative 6. I don't know why I picked green because my graph was in green to begin with, so let's switch to blue. If I connect all of those points, it looks like the graph of my derivative, f prime of x, is just a line. It's a line with a y-intercept of 0, and it looks like the slope of my line is negative 2 over 1, so just negative 2x. Interesting. Alright, so that was just using an estimate. So now what we can do is we can actually use the exact equation of f prime of x to figure out what exactly the derivative would be. Alright, so this is what we were doing yesterday. We know that to find the derivative, we take the limit as h approaches 0 of, and it's going to be our function f of x plus h. Let me just write this out. F of x plus h minus f of x all over h. That's what we need to do. So our function was negative x squared. So here, f of x is negative x squared. So let's do all of our work. We have a limit as h approaches 0, f of x plus h. So our function is negative x squared. But I'm going to plug in x plus h, right? And then we have minus f of x. Well, our function again is negative x squared. So I'm going to just plug in x all over h. Alright, so now we just have to be really careful with our algebra and make sure we do it all correctly. So we have negative, I'm going to leave that there. Don't kill any bunnies or kittens or puppies, so we have x squared plus 2xh plus h squared. Two negatives are going to make a positive, and then we're going to have x squared all over h. So don't forget, we have to distribute this negative through to each and every one of these terms. And when we do, we have an x squared and a negative x squared. What's going to be left behind? Negative 2xh minus h squared. So again, guys, I just distributed the negative through all over h. Oh, and don't forget, we're taking the limit as h approaches 0. Look at that. All the top terms have a factor of h. So let's factor out an h. What will be left behind? Negative 2x minus h all over h. H's cancel out. So now I can actually evaluate my limit as h approaches 0. So h is going towards 0. So what am I left with? Negative 2x. Oh my goodness, isn't that exactly what we got up here? Yep, same. Oh, and look at that. It was sitting right here the whole entire time. Wow, isn't that convenient? Alright, but now you know where that comes from. So now if I actually plug these values into my derivative function, and guys, that's the really important part of this, is when you're looking for the instantaneous rate of change on a curve, it's not always the same. Up here, when we looked at a line, the rate of change is always the same, no matter where you are, because it's a line, it's a linear function. The slope is constant. But if you look at a curve like this, is the slope of this curve constant? No, like I said before, the slope is positive here, it's 0 here, and then it's negative over here. It's changing. You can even see here the slope is a lot more steep on this curve than it is, let's say, right here. Right? So that's the whole idea behind a derivative, is it tells you how rapidly your curve is changing, your rate of change for your curve at any instant. So it's a function. So if I plug my values into my function, when x equals negative 3, I get negative, or let's try positive 6. So yeah, we saw that on our graph. When x equals negative 3, the rate of change is very high. It's a steep tangent line. Right? If I plug in negative 2, I get 4. I'm going to basically get the same exact table as I got over here. We get 2, we get 0, we get negative 2, negative 4, and negative 6. Aha! So now this is hopefully making some sense. Alright, so now we're going to use Sketchpad to show you a more official version of what we just did. So I've graphed the function f of x equals negative x squared. And I'm going to go ahead and figure out a tangent at any one point. So as I as we move x around, you can see how that changes the tangent. So the tangent line can be positive, the slope is positive, then it's 0, and then it's negative. So here's what we're going to do now that's kind of new and exciting. We're going to actually show the value of the derivative at point x, so at any point. So right here, when x equals whatever it equals, the slope of the derivative, you guys see how it's pretty steep and it's negative. So I'm going to plot that value, f prime, right here. And you can see that the slope was negative 1.713. That's the slope of that tangent line. So yep, we're going down to negative 1.713, and we're putting a point there. Right? If I drag x over a little bit further, you guys can see that the slope of the tangent's getting steeper, more negative, so that's why the f prime point is going down. If I drag x over here, oh yeah, the slope is still, the tangent's still negative, but it's not as steep, so f prime is coming back up. If I'm right here, the slope is 0, so that's why f prime is right there at 0. On this side, not very steep slope, right? Positive, so that's where f prime belongs. So I'm going to go ahead and just hit slide x, and you can see the f prime traces out the graph of the derivative, that little point. And if I actually show what that is, you can see it's just a line. And like we saw before, it's the line y equals negative 2x. It's pretty cool, I think. So your job tonight, now that you've watched this little video, is to finish whatever you guys didn't finish in class today with a sub, and then to do this one problem. So we just did one like it. Now this is a little bit more complicated. We have f of x is equal to 1/3 x cubed, but you're going to start by drawing those little mini tangent lines over here on the graph, and do your best to try to estimate what the slopes of the tangents would be. Use a ruler or some sort of a straight edge, put those in there, and then plot those points and see what shape the graph of the derivative has. Then you're going to come over and you're going to use the exact equation. So you're going to use that limit as h approaches 0 of f of x plus h minus f of x all over h. You're going to do that. All right? Notice, don't peek, but it gives you the answers. You're going to fill in the table. All right? Come into class with those notes finished, and then in class tomorrow we'll go through the rest of this crazy stuff. All right? So I'll see you guys tomorrow. Bye!